Let's prove some properties of logarithms by using, we're going to use this fact, m equals log base b of x, or of course b is any base that's allowed. And then n is any other base, or well, same base, but log base b of y gives you n, log base b of x gives you m. Of course, x and y have to be greater than 0. If they're not, then you can't have this. What this means is that from this first one, I can move the logarithm over and I get b to the power of m equals x. And doing the same thing here, I'm going to move this over. That's going to give me b to the power of n equals y. The first property we're going to look at is the product rule of exponents. So what we're going to do is we're going to multiply what's on the inside of a logarithm. In this case, log base b of x times y. So any two things, I haven't specified what x and y are, but any two things, if you multiply them inside of a logarithm, what we can do is we can replace x, right? X is just b to the m. So I get, let's see, log base b of b to the m times, that's x, y is just b to the n, so b to the n power. These are just, like bases that are multiplying. So a rule of exponent says I can just add the exponents together. And now I have log base b of a base of b. So those will cancel, giving me just m plus n. And that, of course, is just log base b of x, right? That was what m was. And n is going to be plus log base b of y. And so that gives me the full product rule, which says take any base of two things that are multiplying, that I can break this thing up into the addition of each one. Multiplication on the inside of a logarithm goes to addition on the outside of the logarithm. Okay, now the quotient rule, I'm going to do a similar type of thing, except now instead of having a product on the inside of the logarithm, I'm going to have a quotient or a division. Okay, we still are going to have log base b of b to the m, that's what x was, b to the n, that's what y was. Here I have a division of like bases. I can combine this into one thing by subtracting the exponents. And then once again, log base b of b, we get m minus n, which is log base b of x minus log base b of y. So the quotient rule of exponents says that if we have a division on the inside of a logarithm, I can split this up into two logarithms that are subtracting. So multiplication goes to addition, multiplication went to addition, and division went to subtraction. This is again based on the fact that b to the m times b to the n is b to the m plus n. Multiplication led to addition, and then b to the m over b to the n was b to the m minus n. Division went to subtraction. Same idea. We actually use these properties in this, in proving this this algebraic situation. Okay, finally, let's look at another rule. The power rule says log base b of something on the inside. I'm going to say x to some power p, right? P is just going to be some, any rational number power, or sorry, any real number power. Now, x is b to the m, right? We haven't changed that fact at all. And power to a power here, I can multiply the powers together. Well, now I have log base b of b. I can remove that and write m times p. I'm going to actually write like this, m times p, sorry, p times m, and m is just log base b of x. And so what I've done here is I've moved the power out in front. Log base b of x to the p equals p times log base b of x. It's an interesting fact that you can just move the power in front of a logarithm. Any logarithm, any base, doesn't matter. Okay, let's expand these logarithms using the properties we just discussed. We're going to expand it as much as possible. So first off, I have a division here, right? 81 is dividing, or x squared is dividing 81. I can break this up into two logarithms that are subtracting. It's going to be the top minus the bottom. Log base 3 of x squared. And now I can write 81. 81 is just 3 to the fourth power. Okay, here I have an exponent on the inside of a logarithm. I can just use this product I just found and move this exponent out in front. This one seems to be fully expanded. I can't do anything there. But this one, right, log base 3 and 3 cancel, giving me 4 minus 2 log 3 of x. And that is fully expanded. Okay, for the next one, I'm going to rewrite this as log base 2 of x to the xy fourth over 16. And I'm going to put this in parentheses and do 1/5 so that we can see the power on the inside there. I can move this power out in front using that property we just solved up here. It's going to give me 1/5. It's actually just times log base 2 of xy to the fourth over 16. Now, I've got a fraction. I can break this up as subtraction. And it's important to note that 1/5 is multiplying this logarithm. So it's going to be multiplying each of the broken up logarithm here. I have to have it in parentheses. 16 is 2 to the fourth power. So this will actually just become 4. This one is a multiplication, right? X times y to the fourth power. So I can break this one up further into log base 2 of x plus log base 2 of y to the fourth minus, this is going to be log base 2 of 2 to the fourth power. That cancels, giving me just 4. So finally we have, I'm going to distribute this 1/5 as well. And I'm going to move this 4 out in front. So we get 1/5 log base 2 of x plus, this is going to be 4 times 1/5. It's going to be 4/5 log base 2 of y minus 4/5. And that is completely expanded, right? We have nothing on the inside of this logarithm here besides x, and this one is just y. So there's no other ways to expand it. Now let's condense these logarithms until there's a single logarithm if possible. First off, I'm going to go the opposite way, right? Expanding was the forward direction, right? This was kind of the expansion. Up here, we expanded by going this direction here. Now for condensing logarithms, we're going to go backwards. We're going to take an addition here, and we're going to make it into a multiplication because that condenses it into a single logarithm. This is going to be important for when we work with equations involving logarithms. All right. So let's condense this. First off, I can move this power in front of the x. It's going to be in the power of the x, not in front of it. And 2 I can rewrite as, right, I can't just change 2 to 7 squared unless I do log base 7 of it. Because then these will cancel and then we give just 2 back. However, I like this because now we have log base 7 there. So I'm going to write log base 7 of x cubed plus log base 7 of 7 squared. We have an addition of two logarithms that have the same base, which means I can combine this into log base 7. 7 squared is 49, and x cubed is just x cubed. And that is completely condensed into a single logarithm. Okay, the next one has log base 10 for all of these. I have a subtraction here, so we're going to do log base, log base 10 of x squared minus 4 over 15. This is minus log x plus 2. And now I can divide again, so we're going to go log x squared minus 4 over 15, and that's going to be divided by x plus 2. Division is going to be division by a fraction, so multiply by the reciprocal. That's going to give us log base 10 of x squared minus 4 over 15 times x plus 2. I can actually factor the numerator. That's going to give me, it's a difference of two squares. So x plus 2, x minus 2. And you can see I can cancel those. So we get log x minus 2 over 15. And that, I would say, is simplest form. Of course, when we do this canceling, right, x cannot equal negative 2. X already couldn't equal negative 2, however, from this, because that would give us a 0 there, and a logarithm of 0 is not defined. So we already had this stipulation from the very beginning. All right, give it a try in number 9. Okay, let's solve some equations that involve these kind of exponential things. So first off, I need to get this to have a single thing here. So what I can do is I can take a logarithm of either side. It doesn't really matter. Let's do log base 7 on both sides. And now I have a logarithm on both sides. So on this side, right, it cancels here, and we get just 2x plus 1. On this side, I have a logarithm of some base with a power, which means I can take this power and move it in front of the logarithm. So we're going to get x plus 2 times log base 7 of 3. Now, log base 7 of 3, this is actually just a number. It's just a number. Plug it into your calculator, and you're going to get some real number. So to solve this, I need to distribute the log base 7 of 3. Plus 2 times log base 7 of 3. And now I need to get the x's together. I'm going to subtract this to this side. And I need to get the numbers together. So I'm going to subtract 1 to the other side. And I get 2x minus log base 7 of 3. X equals 2 log base 7 of 3 minus 1. Okay, I can take out the x here, and then that's going to give me 2 minus log base 7 of 3 times x. This is just the same thing. And then I can divide this out over to this side. That's going to give me, the full thing is 2 log base 7 of 3 minus 1 over 2 minus log base 7 of 3. I wrote it this way because this is an exact answer. But you can, of course, plug it into your calculator and solve. And this gives us approximately 0.08, really 0.09. Okay, The next one, we can divide out 5,000. That's going to make it a little bit easier. And this is going to be 9 over 5 equals 1 plus 14.7 over 365 to the power of 365t. Now, I can, of course, calculate this and give me a base, which then I can take log base this thing. But there's a trick in mathematics that we like to use, and that's the natural logarithm trick. You take the natural logarithm of both sides, and now you have a logarithm on both sides, so we can take this power and move this power in front. That's going to give me 365t times the natural log of this stuff here, 1 plus 14.7 over 365. And 365 is just a number. The natural log of 1 plus 14.7 over 365 is also just a number. So I can divide it out. 365 times the natural log of 1 plus 14.7 over 365. Just divide it out over here. And doing that is going to give us t equal to, well, we can plug this into a calculator and solve that. Let me do that. And that gives me 0.041 just about. It's a nice trick to have. Keep it in mind. We'll use it again. Okay, for this one, I can, I'm going to move the e to the x over and the 132 over. So give me e to the 2x minus e to the x minus 132. And I did this because I can write y equals e to the x, then y squared equals e to the x squared, which is e to the 2x. And that tells me y squared minus y minus 132. This is a quadratic equation. So I can factor it or try and solve it by factoring. Let's see, 132. Right, the AC method says a times c is negative 132 over negative 1. I'm doing just a little bit of work. I can see that if I multiply negative 12 times 11, that's going to give me 132. And if I add it, I get negative 1. So those are my two numbers. And since a is 1 here, I can immediately factor it down into y minus 12, y plus 11. All right, now I can go back, e to the x minus 12, e to the x plus 11. That's what y equaled, e to the x. So e to the x equals 12 and e to the x equals negative 11. All I have to do is take a natural log of both sides. That's going to give me x equal to the natural log of 12 is just approximately 2.48. And the natural log of negative 11 does not exist, right? We have a negative number on the inside of a logarithm. That's not possible. So that answer actually gave us an extraneous solution, kind of like when you have a radical equation with the square roots on both sides, and then you were to square it. It gave you an extra solution. Well, the same thing happens here. We got an extra solution from this process, and so you have to exclude that one because it's not allowed. Okay, let's graph these things and see. So the first one, I'm going to subtract the 3x. Let me just show you it here. I'm going to subtract this thing over to the other side to make it equal to 0. And that's what I have here, this first one. Graphing it, you can see it's a kind of an interesting function. And it looks like it never crosses. It just goes to 0 on this side. It definitely crosses here at 0.09. That was the only answer we got here at 0.09. Okay, subtracting this this whole term over the other side, or subtracting 9,000. Doesn't matter which way you do it. This gives us a very tall function here. The solution is 0.041. And that's just about what we got. And finally, this last one, right, moving everything over, graphing this thing here, that's going to give us only this solution, 2.485, 2.48. Yeah, that's just about what it is. You can zoom out as much as you want, trying to find another solution. This one has a interesting look like that, but it doesn't ever come back up. That's the only solution we get. Give it a try in number 10. Now, those are exponential equations. Let's look at logarithmic equations. Really what we want to do is we want to condense everything down to a single logarithm. Just like how in the radical equations, we wanted to move everything over to one side so that we could square the radical and get rid of it. Here we want a single logarithm that we can take a power to get rid of the logarithm. But always remember, the inside of logarithms cannot have 0 or negatives. They have to be positive numbers only. Okay, for this first one, I can combine this side into a single logarithm. We have like bases, and we are adding, so I'm going to multiply the insides. 2 times x plus 7, or x minus 7 rather, equals log base 5 of 4. Now I can take the 5 to the power of both sides, and that cancels the logarithm. That gives me 2x minus 7 equals 4. Divide by 2. Add 7. That gives me x equal to 9. Let's check our answer to make sure it actually works. Right? This is just a number. This is just a number, so those are both fine. And if you plug 9 into here, 9 minus 7 is 2, and log base 5 of 2 is perfectly fine to do. So that is a good solution. Okay, for this next one, we can combine this side, right? This side becomes log base 2, x plus 7, x plus 1 equals 4. And now I can get rid of the logarithm by taking 2 to both sides. That gives me x plus 7, x plus 1 equals 2 to the power of 4, which is 16. And this is a quadratic equation. Let's expand the left-hand side, get everything over to one side, and go from there. We're going to get 8x plus 7, subtracting the 16 over. This factors down into x plus 9, x minus 1. Double check that, yeah. And that gives us, right, x equal to negative 9 and x equal to positive 1, right? This one's 0 when x is negative 9. This one's 0 when x is 1. Plugging that into here, however, negative 9 plus 7 is negative 2. You cannot have a negative number in there, so that cannot be a solution. Let's check 1. 1 plus 7 is 8. Log base 2 of 8 is actually 3 because 8 is 2 cubed. And here we have 1 plus 1 is 2, right? Log base 2 is just 2 to the power 1. So on this side we actually have 3 plus 1, and that does equal 4. So this is a correct solution. So once again, double check your solutions. Sometimes you can get extraneous solutions as we've seen before. All right, let's graph these things and see them. So for the first one, of course, I subtracted everything over to one side. And the graph of this, it does keep going down here. Decimal just stops because it goes down infinitely fast. It goes down very, very quickly. So it has to just stop at some point. But the solution is where it crosses the x-axis, and that is at 9, which is what we found. Now for the next one, right, -9 was extraneous, so that should not be a solution on the graph, but 1 was the solution, so that should be shown. All right, graphing that, you have 1 here. And you can see over here at -9, it's not even shown at all over here. So that was just created from the fact that we had a quadratic. This just gives us a, it just goes down to infinity at that point. But 1 is the only solution. Give it a try in number 11. Okay, there's one final property we have than just, the product, quotient, power rules of logarithms, and that's the change of base formula. This really isn't that important anymore because calculators can do just fine on whatever base you plug in, but it is useful occasionally. The change of base formula is as such. We have log base b of x. I'm going to change the base from base b to a new base. I'm going to say base a, log base a of x over log base a of b. Now, I wanted to show you the formula because the proof of this one is going to be a little bit weirder, but it's going to be follow along the same kind of ideas that we've shown before. So because we have log, where we said log base b of x equals m, some number m. Now, I'm going to rewrite this as x equals b to the m. And taking this, now I'm going to take log base a of both sides. Log base a of x equals log base a of b to the m. I haven't changed anything, right? I've done it to both sides. But now I can use the property of logarithms that says I can move the power in front. So this gives me log base a of x equals m times log base a of b. I just divide out log base a of b. That gives me log base a of x over log base a of b equals m, but m is just log base b of x. And there is the formula right there. It's important to note that the denominator of the change of base formula is log base a of b. A and b are just given numbers. Normally, when you're doing this in practice, x will have some variable in it, but b and a should both be given as a single number. So that's just a number on the bottom. And we normally change the base from some unusual base, like some maybe like 86.593, and some random decimal base, to bases with e or 10, because those are always the nicest ones to work in. Now, let's look at one in this case, log base 0.3, that's an unusual base. Let's change it to base e. So how it works, you're going to change the new base, log base e, or what I should write is the natural logarithm. On top goes the inside of the logarithm, so we have 19. And on bottom goes the previous base, 0.3. This is, of course, also equal to base 2, log base 2 of 19, over log base 2 of the prior base. So that's the change of base formula in practice. Give it a try in number 12.